Okay, go ahead.
Very good. Welcome back to Chapter 14, NMR, Part 3. This is Monday, April 6th, this video. We will be finishing up this chapter, I believe, in this class period. So homework 14 for this chapter will be due tonight. Make sure you upload that. And quiz 9 is on the NMR topic. It's on Learning Suite. It's 4 pages. Make sure you get all 4 pages and get your best answers on there. Use scratch paper if you need to. We will just be grading your solutions to the problems concisely drawn out there and written up on those 4 pages. So make sure you upload all 4 of those. That's due on Wednesday. And we'll have the beginning of Chapter 15, Radical Chemistry, starting on Friday. And that will be our last chapter coming up. A couple periods on that. And then, of course, we'll have Test 4. Again, multiple choice format. And then we'll get ready for the final coming up, which is also going to be multiple choice that way. But sample test 4 is already on Learning Suite if you want to study ahead there. And there is a sample final that I have on Learning Suite also. So last time we were starting to solve problems and do a lot of peak assignments. Let's go over here to the board first. And this is a nice little review. And this ties in with data that we went over in Chapter 13. In fact, this was the problem in Chapter 13. Propose a structure for this data here. The mass spec, 88 and 57, where 88 is the molecular ion peak. That's the molecular weight of the intact molecule. 57 was the base peak, the major fragment. And the IR data for this compound was 1710 in the inverse centimeters there. So what does this say? We've got a carbonyl, okay, 1710. And we came up with a molecular formula. Review that in your notes from Chapter 13 to see how we came up with C4H8O2. Notice we have, 1 degree of unsaturation there, C4 and H8. In O2, it's probably the carbonyl there, of course, and most likely an ester, okay? But it doesn't have to be. Here are 4 proposed structures, and now by NMR, we have the ability to tell these 4 apart. And there are some other possibilities here, but I'd like to focus on these 4. And we'd like to go through an exercise to begin with now. Can you propose what delta values each non-equivalent set will have in these molecules? Where will the shift be? How many, integration-wise, how many hydrogens in that set? And what will be the multiplicity? Remember, these are the 3 main pieces of data that need to come out of proton NMR that help us determine structure. So let's just go through them. If you want to pause here and see if you can go through that and assign each hydrogen set in these molecules, both the shift, integration, and the multiplicity. Okay. Now we're back. Let's go through it here. So this would be about 2.5 alpha to a carbonyl. The integration would be 3, and what would be the multiplicity? Singlet. Okay. What about this one here? This would be, about 4 ppm, and there'd be, 2 hydrogens, and it would be what? With 3 neighbors, it would be a quartet. This one here would be, around 1.5, maybe 1.5. It'd be 3 hydrogens, and it would be what? A triplet. Okay. So that pattern there, this line listing of the data, is consistent with this type of a structure here. We'll have to look at the actual NMR spectra to see how close we are. And I have those. We'll go through those in a minute. Let's just compare the rest of these here. So we'd have a similar thing here where we have an ethyl group, so we'll have a triplet quartet. This one will also be around 1, let's say 1.2, 3 hydrogens, and do the triplet. This one here, alpha to the carbonyl, 2.5, 2 hydrogens, and a quartet. And this one here, around 4, 3 hydrogens, and no neighbors, so indeed a singlet. That's very distinct from this one, right? The two different esters there. Here are the ethyl groups over on the side, alpha to the carbonyl. Here the ethyl is on the oxygen, so that's a little shifted further downfield. That's a common mistake some students do when they get used to some of these patterns, quartet, triplet, big doublet, small multiplet for an isopropyl, for example. It's getting the position of the functional group. And esters are kind of common this way. We can flip the ester around either way, and that'll give a different shift for the groups on that side. How about this one here? This is also C4H8O2, but what do we expect here? Here we've got the hydrogen attached directly to the carbonyl. And if you remember that, that's way down at 9 ppm. And of course it's one hydrogen, and it's a singlet, no neighbors. Okay. This one here, again about 4, be 2 hydrogens, and be a triplet. Okay, so that's similar to, which one did we have? We had a similar one at 4. No, this one was a quartet. Yeah, so this one only has 2 neighbors now. Yeah, it's a triplet, so that's distinct. So this is a propyl fragment. It's going to be different there. What about this one here? It's going to be about 1.5, 2 hydrogens, and how many neighbors? 1, 2, 3, 4, 5. So it'll show up as a hextet. Okay, so it'll be a complex pattern. Or maybe it'll just be a multiplet. You can just say multiplet there, if it's a complex multiple spin system pattern. What about this one here? Yeah, about 1 ppm, 3 hydrogens, how many neighbors? 2, so triplet. Again, a propyl fragment. And notice this one has what? 4 sets. These others just have 3 sets. So sometimes you can tell just from that. Then this one here looks kind of funny. It's a ketone ether. It's not an ester, but it's also C4H8O2. And it's very distinct, I think. So this one, 2.5 or so, what, 3 hydrogens, and indeed a singlet. What about this one here? Well, it's alpha to the carbonyl and this oxygen here. So this one will be shifted probably down around 5. Remember, those effects are additive. If you're next to multiple heteroatom groups, you're shifted further downfield. And then 2 hydrogens and still what? Singlet. This one here, about 3 ppm, 3 hydrogens, and indeed a singlet. Notice they're all singlets there. So how'd you do? Did you come up with some reasonable shift values? And the amounts are easier to do, just counting up the hydrogens. But again, the number of those hydrogens, that's why we emphasize that, is then a factor in determining what the multiplicity. So it's important to add up those numbers. Well, let's see how you did. Let's go over to the screen up here, Isaac, and let's see what we got. We've got the thing we left off with in part 2 for 14, where we did this vinyl acetate, and we went through all the assignments there and the couplings. That's a tricky one. This terminal alkene, has the 2 hydrogens on the end, which are different. These are technically diastereotopic, you could say. And so they have coupling partners and shift positions that are different there. And this HD was this one furthest upfield. And then we had this double of doublets where we saw the large trans coupling here and the smaller cis coupling. And I think this next graphic, I didn't show this one last time. This emphasizes that you can see the 20 or so hertz here. Now they're saying 14. I think we said 20 and 6. I don't know. Look back at your notes. The large one we do first into a doublet, and then the smaller doublet here is the cis one, about 7 hertz, 6 hertz, whatever. You see the double of double there. That's for this one, HD. And then you still see that large coupling here, and then the small geminal coupling between B and C is smaller. What's this 1.2 hertz, very small. And then you see the cis coupling here of 6, and then the small geminal coupling also there. So you see the couplings in multiple places. That's another way to verify. All right, let's see the data on, the ones we just did there. This is combining with the mass spec IR data from chapter 13. All of these are consistent with that data, although this fragmentation, this 57 here, is actually this cleavage right here on the acyl position And that acylium ion for this methyl propionate ester is actually the one. But you can tell all these apart, right? You see the triplet quartet here for the ethyl group right there, and then a singlet for the methyl right there for that ester. That's certainly distinct from this one, right? And then we have this formate ester right here, this propyl group. You see that complex pattern there. There's our multiplet for the methylene right in the middle. It's a 6-line pattern. I think you can see that. Okay. I've got the line listing here for each one, and this is how you'll fill out the data on quiz 9. And this is the convention for the line list. You always have the delta value first, the number of hydrogens, and then the multiplicity. Okay, so when you do assignments on quiz 9, you'll see how that is. And that's how it's reported in a lot of the homework problems as well. And here's this distinct one, all sharp singlets. Okay. So, given the choices here for this data, all of these can be easily determined from each other, being distinct patterns, distinct shift values and multiplicities in the NMR. All right, very good. Let's continue here with a review of this molecule again. We used this early on in a couple spots, the first 2 class periods, ethanol, of course. We've got our characteristic triplet quartet here. For the ethyl group, notice the quartet is furthest downfield. That's one alpha directly connected to the oxygen, more de-shielded, right? It's got the 3 neighbors, so it's either quartet. Then we got the singlet here. That's what I want to talk about a little bit. Under these conditions, I think this was a 300 megahertz instrument. I don't know what the conditions were. It's probably deuterated chloroform conditions. The purity of the sample must have been pretty high because this peak is pretty sharp here. But notice that's still a singlet, so there's a lot of hydrogen bonding going on. There's no coupling to these neighbors over here. So we normally do not see J coupling or splitting due to the presence of an alcohol being present there. If that were coupled, we'd expect that to be a triplet, but it's not, okay? Oftentimes it's very broad. This signal shows up quite sharply. You can treat an alcohol with D2O, deuterated water. You can just shake it with water and then re-isolate the alcohol. Now the alcohol, instead of having hydrogen there, will have a deuterium there. Now deuterium is a diamagnetic atom. It's not active in the NMR. So this peak here would go away if this was deuterated alcohol. And I'll put that structure, and we'll go back in a minute, but that's what the structure would be. The deuterium would be on the oxygen there. Okay. Another molecule we showed you last time, or a time before, I forget, it was chlorocyclohexane. And you see it's certainly distinct from just hexane itself. I like to show hexane because all 12 of these hydrogens are the same. And they're all exchangeable by symmetry, so they all resonate at the same place. It's just one set. There's no coupling here. You only see J coupling or splitting if they're different, distinct sets. So this is just a single resonance at what point 4 is that? Just alkyl position. The methylenes typically are a little further downfield from 1. Methyls are usually right around 1. Methynes are usually about 1.6 or 7 or so. Okay. And then we've got the chloro. Cyclohexane, the first thing to notice is alpha protons way down here. And how many neighbors? 1, 2, 3, 4, 5. 1, 2, 3, 4. And then n+1 rule, right? And there you see it. There's a 5-line pattern for those there. Now, we talked about if you draw the chair conformation here with the chloride in the equatorial position, you can actually see more complex patterns here, but these kind of all bunch up here. All these signals here, this one here is coupled to a lot of things next door. We just call that a multiplet if we determine the structure. Multiplets here, a lot of overlap there. So yeah, just multiplets. We can't really say much else about that molecule. And that's okay. This alcohol here I wanted to show you here, and this is the difference between 90 megahertz, which is an older instrument in the old days here when I was a graduate student. I think I worked on a 90 megahertz. Then we finally got a 300 megahertz machine. That was a big advantage, better resolution. Here's a 400 megahertz machine. We have one of those. We did have one of those at BYU. Here we have a 300 and two 500 megahertz instruments. We used to have a 200. we decommissioned a while ago there. Here you can kind of see the difference in the two spectra. They all show up at the same spot, but there's better resolution here when you have a higher field instrument. So notice this big blob here from 1 to 2 really separates out nicely here at 400 megahertz. You can begin to see here that this position here is alpha to the oxygen at 3.5. This is the OH group here, and then we've got 2, 2, 1, 4, 1. And I kind of show you the assignments here. You can look through that. Again, you have these graphics, so you can do that assignment there. But that's the advantage. Lower resolution, higher resolution here. Remember what this means is between a 1 ppm unit, you have in hertz what the megahertz of the instrument is. So from 1 to 2 here, we have what, 90 hertz. Okay? So whatever those couplings are, you see they're crammed together. But here at 400 megahertz, from 1 to 2, we have 400 hertz units. Okay? So that allows these to separate out better and have better resolution between those. And of course at 500 or 600 megahertz, commercially now we're up to 900 megahertz instruments, which are typically used to do protein structure determinations, where you have a lot more signals and you need to get even better resolution. Those are extremely expensive instruments, $3 to $4 million instruments. Ours are cheap ones. They're only about $1 million a piece. Anyway, okay, let's look at a couple other things here. Aromatic shifts. And I think I mentioned this one. Monosubstitute benzene around 7, and they're often crammed together. This is at 600 megahertz, so they are separating out quite a bit. There's 1, 2, 3 distinct sets on the benzene here. These two, the ortho positions we call next to the group that's substitute here. And the next position is called the meta position, and then the opposite position is called the para position. And so we have 3 distinct spots. A lot of times it's just alkyl benzene. These will all have the same shift. They'll all be piled on top of each other. Sometimes with low field instruments, it'll even appear as a clean singlet. But if we have an aldehyde, so benzaldehyde, or methoxybenzene, anisole here, we have an electron withdrawing group. We can draw resonance structures. Those resonance structures have what? Partially positive group at the ortho and the para position. And I'll go to the board and show you that in a second. Or with a methoxy group by resonance, these lone pairs can actually donate into the ring, and we have a shielding effect, which makes these resonate at lower frequencies, a little more shielded. So these are around 7 or high 6 if we have a donor group. If we have a withdrawing group, the ortho and para positions are pushed downfield toward 8. Okay, so we'll have to look at those resonance structures to see that effect. So a lot of times you can see them split out, and you can do the peak assignments, but not always. So here's a real structure here. We've got phenyl, ethanol, we call this. We've got the benzene on the same carbon as the alcohol, so this is now methine carbon. That's going to be far downfield. Well, let's look at the aromatic first. So we've got the 5 equivalent aromatic ones, and there they are, all kind of piled up. We see a little bit of coupling there, but again, that's 5 hydrogens. If you do the integration, sorry we're not showing it here. A lot of times the integration we do separately will give you how many hydrogens here. Oh, you'll see the lines drawn. This is the second experiment, and the height of those lines determines the integration there. But yeah, so 5 hydrogen there, 1 hydrogen here, the quartet, that's right there with the 4 neighbors. Yep. And then here's our alcohol peak, the OH group, that if we shake with D2O, will go away. And then we have the doublet here for the methyl group now. So it's not like the ethyl pattern, which was quartet triplet. This is now what a doublet quartet, or that kind of a pattern there. But that lets you see how that looks. Here's a good one. So paranitrotoluene and pyranitrotoluene, we see the nitro group here and the methyl. So the methyl shows up here at 2.3. It's a singlet. And then we have these 2 doublets down here. So if we're ortho here to the nitro group, that's a withdrawing group. We draw resonance structures there showing a positive charge at the ortho positions. So, and they have 1 neighbor, okay, and it's equivalent on the other side. So it's the same. So this one way down here at 8 is a doublet. That's the one ortho to the nitro, the withdrawing group. And then ortho to the alkyl group, which is electron releasing, is up here at 7.3 doublet, where you expect it. But often we see these two quartets down here for this para-type splitting, which is very common in aromatic compounds. Now, well, let's go down here to the board first. Let's don't go to palaomine yet. Let's see here. So, what we said here a second ago on ethanol, we showed the full spectrum there. We could see this proton, even though it's broad and no coupling, always a singlet. If you shake this with B2O, which is deuterated water, and we can get 100% of that heavy water, it's called. So big excess, shake that. These are what? Hydrogen bond exchangeable. And so you re-isolate the alcohol, and now it's just this. And now you just see the two sets in the NMR, where here we saw the three. Okay? So you can often tell if you've got an alcohol element. Now let's look at this one. Do the resonance structure here. We have benzaldehyde, and these were around 8 or high 7 ppm. I forget, what was it? Let me double check there real quick. Well, we didn't, no, yeah, there were 8, that's right. Okay, yeah, you don't need to go back. So why are we around 8 ppm here for this hydrogen? Question. Well, let's draw a resonance structure. Remember, carbonyl, we can draw this type of resonance structure, right? So we've got the carbonyl like this, and plus charge right there, right? Okay, well, we're closer to a plus charge here, but what does this look like here? We've got a double bond here on the side, or the side there. We can draw a resonance, of course, with the benzene. Let's go ahead and draw another resonance structure and push the electrons toward this positive charge, okay? And so what do we get for the other resonance structure here? We get a positive charge right on that carbon where that hydrogen is, right? So if there's partial positive charge here, what does that do to the shielding of this hydrogen? Well, it's withdrawing electron density. Remember, electrons help shield nuclei. And the more shielding we have, the higher, or the lower the frequency toward TMS. But if we have less electron density around the hydrogen atom, the nuclei is more exposed to the external magnetic field, and it's shifted to what? A higher frequency, which is downfield from that. So these type of resonance structures, and we can resonate the plus charge over here also, right? Just keep pushing the electrons around. Or if we just move the electrons here, we'd also have a plus charge here. So the ortho ones and this para one are often shifted downfield. Now the other one was the anisole methoxybenzene. And there you might say, well, this oxygen is electronegative. It's electron withdrawing too, just like this one here. But through the pi system, the lone pairs on that oxygen are actually electron releasing. They're donating electron density through the pi system framework. So this resonance structure going this way is the more important one now. Let's draw the result there. I think you'll see these methoxy ones are shifted what? Further upfield because of this. You can see by donating a lone pair here and pushing electrons down there, this becomes what? Partially negatively charged. There's more electrons shielding this hydrogen, and they're shifted toward a shielded position, which is at a lower frequency toward TMS. Okay, so that's the difference there. These are shifted to higher frequencies, being more deshielded. These are shielded and require lower frequencies in order to accept them. Not by much, it's just a little bit. This is toward 8, and those, if there's a donor group on the methoxy, further up there. Okay, let's go back up here and look at the screen. And what we got is a very complex looking molecule. Look at all those nitrogens in there. Palaomine is the name of this natural product. It's isolated from a marine sea sponge. It has anti-cancer activity and a number of other biological activities. And a lot of new natural products, once they're isolated, they're shown to have some activity in a cell-based assay. So we can determine that there's something in that biological sample that has some beneficial biological effect. This was discovered using one of these anti-cancer cell-based assays. But that says nothing about the structure. So you have to purify enough of it out of the sea sponge and then do detailed NMR experiments in conjunction with X-ray analysis and other analytical tools, mass spec, IR, of course. And this helps us see how many atoms we have, what's the molecular weight, and what are all these spin systems in the proton NMR. So you can count up all these positions here and determine this. And this problem here is we're asking how many peaks are observed with proton NMR for each of the red signals. So what's the multiplicity of these red ones? So let's look at HA here. And it's alpha to chlorine, so it's probably around 3 ppm. And then how many neighbors does it have in the next over carbon? Well, there's a hydrogen here. This is a methine hydrogen on this carbon here. So it would be a doublet. Notice there's no hydrogens at this quat center. Okay, so a doublet about 3,5 there. What about HB? Well, that's a methine one. How many neighbors there? None. There, none. Oh, one there. Again, another doublet. Okay, and it's alkyl here, so it's probably around 1.8 or so ppm. So you can kind of see how different pieces might be. And how about this HC here? Well, it's on a nitrogen. That's an amine. So directly on this nitrogen, it's hydrogen bond exchangeable. So this will be a broad singlet for these two, even though it's next door to these two here. So probably just a singlet there, okay, like we said with hydrogen bond. What about HD here? Well, it's got another hydrogen on it here. This is a methylene hydrogen. But what about that methylene hydrogen and HD here and this hydrogen here? What's their relationship? It's right there, diastereotopic. Those are positions here. If you exchange them both separately with deuterium in that thought experiment, you'd have a pair of diastereomers. So these are diastereotopic. And that one's up here in this concave position of the molecule. This one's convex out in another position. So magnetically, they're not equivalent. They'll have different shifts completely because there's a lot of stereocenters in this chiral molecule here. So diastereotopic here. So it is coupled to this one in a vicinal manner, a doublet, and then it's also coupled here as a doublet. So this will be a doublet of doublets. And you could do that similar analysis to the whole molecule. Now this is a very complex example. This will not be on the test. I just like to show you how these principles apply to something a little harder. And this is much, much harder, right? Look at all these signals for polaramine. They're all nicely spread out, which is kind of cool here. You can actually do a peak assignment for each one, and the coupling patterns help you tell which one is next to which. You see some singlets here which stand out, and that's very helpful as well. And the position, of course, tells you a lot. We can focus in on this 3 region here and just say something about that as a follow-up with the molecules we were just talking about. So let's look at the ones that are resonating around 3 here. We've got a couple here. A 3,5, let's see that position. Oh, 3.52, so this actual shift is right here, center right there, 3.52, there it is, and it is indeed a doublet of doublets, these two right here. And there's the doublet of doublet pattern. Kind of looks like a triplet, but the 2 lines in the middle are overlapping, and you see another little line there, just the shoulder of it, doublet of doublets for that red edge. What about these here? There's others at 3, I think. There's, this other one, the diastereotopic one's at 3.27. They're often quite close to each other shift-wise. But that's also a doublet of doublets. It's right here. You can see it, it's kind of buried under this doublet. There's a bigger doublet here. Where's the other one that's a doublet? Let's see, see that one? Where is it? Oh, right here, this HD doublet, yeah, 3,3. That's also right there, doublet, there it is, okay. Those are the only ones showing up, I think. But the other positions can all be assigned there. You see them all in blue. Anyway, don't let that scare you. I'm just showing you the applications of what we can see there in that type of a molecule. Oh, and this one here, this ties into chapter 13. This was the attention grabber there. THC from marijuana, cannabinol, and spice, the synthetic marijuana compound. Remember I told you about the sad experience in the ER emergency rooms in Germany, a number of people dying from this. Originally they thought they had high levels of THC in their system. But no, it turned out to be this compound, spice. And they had to isolate enough of this material and do the NMR. Notice the two NMRs here for the two compounds are very different, right? Spice is dominated by all this aromatic signal way down here, whereas tetrahydrocannabinol's got a lot of alkyl stuff in it up here. And I include the biological data here. The synthetic marijuana or spice binds very tightly to the cannabinol receptor, CB1, 9 nanomolar. It's about, 4 times more potent than THC for that, which is 40 nanomolar. Now that's very potent also. Nanomolar concentration is 10 to the minus 9 molar. So any concentration above that, these receptors are saturated and you're eliciting the effect there in the brain. So very potent compounds, not things to be messed with. But the full data there, the molecular weight, the mass spec, along with the NMRs, help determine those structures there. All right, let's go on here and do a couple problems. So these are from the back of your book. The numbers might move around a little bit, but let's look at that problem right there. See if you can do that one. Pause it if you'd like to. And let's see. We are back. So what do we determine for this structure here? Well, we've got the singlet up here at 3.5. We've got triplet quartet, and we've got C4H8O2. Well, you should be expecting something here. It looks like what problem we just did, which is this. So let's verify this structure again. So if you come down here, you got that, Isaac? Okay, so what do we see here? We saw quartet, we saw triplet, and this quartet was up at 2.4, 2.3 ppm, and this was 1.2, yep, where the triplet is. So our ethyl group's on this side of the carbonyl, right? And then we have this singlet at 3.6, okay, for 3H. And that's alpha to the oxygen, so that's further downfield. So what you may have tried to do here for this molecule is maybe this. Very similar, those two esters, right? But notice the ethyl groups here on the alkoxy oxygen part. So this one here, instead of being at 2.3, this one would now be what? At 3.5 or 4. So that's much higher now. This quartet being at 2.3 for the correct structure, you see, is lower. If you had this structure here, this would be too high for that methylene position. Okay, so that's a little bit of a difference there. And also this one here, this singlet here, instead of being at 3.6, this one's at 2.4. It's just alpha to the carbonyl there. Okay, so there are often some very distinct things, and when you work a problem, go back and double check it and make sure it's internally consistent with all the data. Because a lot of times we come up with a structure that will be consistent with the mass spec or the IR, but not with the NMR, with the details of where the shifts are. Even here, the multiplicity patterns are correct, but here the shift things are just a little bit off. Okay, so double check that. You should be okay for that. All right, let's do another one here at the board, which is maybe a simpler problem. I don't know. Well, let's see if we can do it here. We've got 4.0. We've got a multiplet, 1H, and at 2.4, we've got a singlet, also 1 hydrogen. And let's see, at 1.2, we have a doublet that has 6 hydrogens. Okay? And that's all the data we're going to give you. Well, maybe the IR. Let's give you some IR data. 3,300 inverse centimeters. So what can you tell from the IR right away? 3,300, oh, and by the way, it's broad. And it's very strong. So what do you know already? Alcohol, very good. So that's one you should know. You work enough problem, you'll see that. On your test 4, I'll give you a data sheet that will give you some characteristic IR frequencies, stretches that correspond to important functional groups. But I think you'll do enough where you'll figure this out. Let's see here. So what do we got? We've got an isolated singlet. And by the way, this one will exchange with D2O so you won't see it. It'll go away. So this one's exchangeable here. Multiplet, doublet here, and maybe let's give a little more data for this. This peak, if we do it at a high resolution, can we see that signal? Let's see, it turns out to be a heptet. Okay. And we've got a pattern here. We've got heptet, doublet. These are the only things coupled to each other that have any coupling. This is a singlet there. And that's probably what? Our alcohol. Okay? So you can already tell something there. Notice I'm not giving you the mass spec or the ratio of atoms. So sometimes we can leave that out if it's a simple enough problem. Another thing that gives us away is the 6 hydrogens here. Now there's no carbon that has 6 hydrogens on it, right? Well, what does this look like? 2 methyls, right? That's probably what it is. And 2 methyls with 1 neighbor. So here's our methyl, CH3, and here's our other CH3, and it must have 1 neighbor. So you can kind of go backwards here, okay? 1 neighbor, so N must equal 1. So that kind of helps you figure this out. And 6 hydrogens, 2 methyls there. So this fragment here must be in our molecule. And that's really the only thing where we see the couplings going on. So what else do we have to stick on this structure? So this is kind of this putting fragments together approach to solving the problem, kind of a reductionist approach here. What are the individual parts, and let's kind of stitch them together. What else do we need to put on there? Oh, our OH group. Let's see. That's consistent with everything we know about the structure. And indeed it is. Let me give you the rest of the data in the mass spec. It's 60, okay? So what is our structure here? 1, 2, 3, C3. H, how many? 7, 8. And O. And does that add up? Yep, C3H8O has a molecular weight of 60. So everything's consistent there. The IR, the mass spec, the NMR. Does that make sense? That problem there? All right. Before we do another problem that's on the graphics here, let's write out the data here on the board and maybe get started on it. And then I'll turn you loose and let you work on it. So here we've got a problem, 1.2 delta. It's got an integration of 9, and it is a singlet. Then we have 1.3 delta that has 3 hydrogens in it, and it is a triplet. And then we have 4.1, which has 3 hydrogens also. And, no, sorry, 2 hydrogens. And it is a quartet. Let's see, I'll give you the formula here. C7, H14, O2. Okay. So you could add up this and see what the molecular ion would be in the mass spec. Let's see, should I give you an IR also? Okay. IR data, 1710. There you go. So from that line list, could we begin to piece things together? 9 hydrogens, 1.2 singlet. What does that look like? Before we do that, let's look at some of the basic patterns. Okay, basic patterns. And these involve multiple spin systems, but they're so common for simple molecules, I think it's good to list them all together. So if you just have a methyl CH3 and it's isolated here, it'll be a singlet. So as long as it has no neighbors, that methyl integrating for 3 hydrogens will be a singlet. You can say, yeah, probably got a methyl there. And ethyl. So we've seen this over and over again, right? 2 and 3 hydrogens, and what? We've got a quartet and a triplet. Okay, so if you see quartet triplet, you've probably got an ethyl group. Now there might be another thing coupled here which would make that more complicated. So these are really for insulated systems where there's no more splitting, no neighbors on the left side here. And anyway, methyl ethyl. What about isopropyl? Again, what would this be? Well, it would have 1 hydrogen, And then the 2 methyls the same, we just saw that pattern, 6, 1 and 6, and what? Multiplet, and then doublet, big doublet, okay? So big doublet integrating for 6, and a little multiplet for 1. Probably got a isopropyl. Well, I think you can see this coming. What about this guy? Tert-butyl, very common group. How many hydrogens? Well, all 3 are the same, homotopic. 9 hydrogens and what? Singlet. There's no neighbors. You've got this quaternary carbon there. So if you see a big singlet for 9 hydrogens, guess what? You've got a tert-butyl. Okay. So what do we got here? We've got a singlet. Oh, 9. Okay. So what do we probably got? Okay. Let's do our reductionist approach here and add these things up. So we probably have a tert-butyl. We have here triplet quartet. And these are the only ones coupled together, right? And so what do we got here? We've probably got a good old-fashioned ethyl. And a lot of times you can just come up with a couple fragments from these line list data and see how it might go together. Now you got to experiment with it to see how it comes together. We've got 2 oxygens here, so what else do we have? We've got an ester. So from that data, we can say ester. Okay? Now, take a minute and put these guys together and see what you come up with. Isaac's got a question first.
With the IR data, could we say that it has a ketone and an ether?
Yeah, so we may not know if this is an ester or not. We just know we have a carbonyl probably right now. But some other data here, you know, shift-wise, might tell us what type of a carbonyl, or maybe it's just a ketone. It's not an alcohol. We might think, well, we've got 2 oxygens, at least from this. We don't have the alcohol for the IR. So it's often some assumptions we make, and I'm assuming it's an ester right now. May not be, though. You're right, Isaac. But take a minute now, pause things if you need to, and see if you can put together the real structure. Okay. And we are back. Let's see what we've got. So, yeah, I think the ester is consistent. Let's see if we can build something there with the ester first. And this shift right here, being at 4.1, 2 hydrogens for the quartet, that's where our ethyl probably begins. So I put the ethyl right there to give that a shift of 4.1. And indeed, it's a quartet, and then this one here is attached, being a triplet. So where does the tert-butyl have to go? Well, probably back here. Okay, big singlet for 9. Let's see if we're right. We got the data up there. Oh, here I wanted to show you at first how this question is posed at the end here. It gives you the formula, and look, it gives you the multiplicity here, not the absorption. I'm not sure what that, this is multiplicity. ppm, the delta value right there, and then the integration. Remember, this can be arbitrary. So this one just gives you 26, 10, and 6. So what you need to do is play around with these numbers. 26, that's about 3 times this, 10. So that might be 3 to 1. But would this be also 1, 1 to 1 to 3? That's a little bit low there, that's 6. But if we say that that's 2, then this might be 3, or that would be 6 to 9, right? And then 9 times 3, 27. That kind of makes sense there. So it's really 9 to 3 to 2. But you can experiment with that. The lowest one sometimes is 1 indeed. And then you just divide that number into all the others, but you'll come off a little bit off there if you assume that's 1. But if you do the math and kind of play around with these numbers, you see it really integrates for what, 2 to 3 to 9. Okay? Those numbers are often arbitrary. Anyway, so let's see if we got the right thing. That's just restating the data. Ah, and there it is. Okay. We've got the mass spec, 130, which is for that formula. 1710, yeah, for the carbonyl. And then the multiplicity patterns. And the shift position really tells you that that ethyl has to be down here around 4. Okay. Questions on that? Very good. Let's go on to this, which is what? C13 NMR now. Yes, there are many other NMR active nuclei. We can retune the frequency of the instrument and set up the detector to observe different positions within the NMR spectrum of the frequencies. And C13 is shown here for acetic acid. And how many carbons do we have here? Well, we have 2. And what you notice right away here is the ppm range. We're going from 0 ppm all the way up here to 200. Well, we normalize TMS, tetramethylsilane, also. All 4 of those carbons in TMS, we have at 0 again. And what do we have here? We just have a singlet here and a singlet there. We often see no coupling in C13 NMR because it's always proton decoupled mode, either broadband or off-resonance decoupling. That's always turned on, so you don't see the coupling to hydrogen. Sometimes in the hydrogen NMR, proton NMR, we see coupling to C13, but C13 only has a natural abundance of what? 1.1%. So normally we don't see it because of the probability of that hydrogen being on a carbon that has the NMR active nuclei. C13 is not very high. They're always on C12 carbons. But here we're looking at the C13 of the NMR, and what you see is that the signal to noise is poorer. You see a lot of other little jagged peaks here in the observed channel, and that's because the sensitivity is much lower now due to the low natural abundance of C13. Yeah, so the other thing here is the carbons actually respond differently coming back into resonance once the RF pulse goes by here. So you can't integrate C13 or compare the heights directly. So there's no way to do that. If it's a highly substituted carbon, a methine carbon or a quat carbon, sometimes their intensities are quite low. Sometimes you can do that. And there are other experiments to determine methyl from methylene methine carbons, but we're not going to go into those details. A lot of other NMR type experiments. What you see here is just the 2 different carbons. One way up here toward TMS for the methyl, and the carbonyls down here at 170 or so. So that shift range is about the same for protons. It depends on hybridization and being in proximity to electronegative atoms. So down here is the alkyl region, or alpha to heteroatoms, 30 to 80 or so ppm. Alkynes, pretty broad range here. Alkenes, a little over 100. Aromatic, well over 100. Carbonyls are usually the furthest ones downfield, down toward 200, which is an amazing thing, I think. And that's because of the resonance here, right? So partially positive carbon is going to make that more deshielded, and higher frequencies are going to be needed to resonate that. Let's just look through a couple samples here. Everything applies to symmetry that we've talked about before with proton NMR. So how many non-equivalent carbons do we have for one propanol? Yep, we have 1, 2, 3. And the furthest one downfield is going to be the one next to the oxygen there. Okay? The other 2, sometimes hard to tell apart, but there are other ways to do that actually. Here's this ester here. The ester carbonyl is way downfield at 170 or so. Alpha to the oxygen right there, that methyl will be right there. And then the other methyl right here, alpha to the carbonyl is right there. What do we have here? We have the secondary alcohol, which has 1, 2, 3, 4 carbons in it. And there they are, 1, 2, 3, 4. So pretty straightforward. I like this example. So this ketone here has 2 ethyl groups on it. So symmetry-wise, there's a near plane symmetry right through the carbonyl. So the 2 ethyls are equivalent. The 2 methylenes resonate at the same spot. The 2 methyls at the same spot. So how many total carbons do we have here? Right, just 3. 1 for the methyls, 2 for the methylenes, and then 1 for the carbonyl. So keep in mind symmetry. Sometimes that comes up in problems and can be kind of tricky sometimes to see. I wanted to talk about MRI and 2D NMR just very briefly. If you're interested in medical imaging, some of you probably had MRIs taken of you. It's very good for soft tissue visualization. This is 2-dimensional NMR using proton and phosphorus 31 NMR. And these are 2D slices through living tissue. So you're put into the big donut here. So the magnet is this whole thing around the patient as they slide in there. And you're moved along, and you can feel the different magnet frequencies being tuned. There's a lot of clanging and noise. Sometimes more modern instruments don't make as much noise. They're a little less intimidating. But you got the claustrophobic effect, and then you have the daunting name here, NMR. No, they don't call it nuclear magnetic resonance imaging. It's the more kind of gentler term, MRI, right? So magnetic resonance imaging, no nuclear in the title there, even though it's the same principle. And these are 2D slices, so there's a computer tomography effect that assembles those slices, and it's the density of the signals between protons, which is you have a heavy aqueous solution, tissue area, which is rich in protons. You'll see a lot more signals for the hydrogen. And if you're in heavier tissues, you see a lot more of the nuclei, you see a lot more phosphorus. So the calcium phosphate structures, and as well as the nucleus has the DNA, RNA has more phosphorus, P31. P31 is also a very active NMR nucleus. And there are other types of imaging that use other nuclei, but this is the main one. And this is a two-dimensional image. This is just one slice through the middle of the spinal column here. And you see the softer tissue here is the spinal cord. And you can actually use this diagnostically. I think these are the pads between between adjacent vertebrae, right? And what do you see here between the vertebrae? You see a rupture zone where some of this tissue is leaking out right there. And that may correspond to a back problem that this poor patient might have. But you see a lot of anatomically significant structures there within the MRI. Based on the same principle, but different nuclei, proton and phosphorus. All right, let's look at another 2D NMR technique. And when you take 353, the lab class, Dr. Bronson will go over this a lot more. This is COSY, or correlation spectroscopy, where we're correlating the hydrogens within a molecule to see which ones are coupled with each other. Okay? So this lets you see which ones are coupled. You run two experiments, one regular proton and another regular proton here, and you let the spin systems correlate. Now, I'm not going into the details of that, just what the data shows here. The off-diagonal blobs here, these are actually peak structures. They kind of look like topology maps for hiking around. You see the mountain peaks, the elevation gain, whatever. And that's actually what these are. You could say that's how the processing of the data goes. But this peak right here correlates this red thing with this off-diagonal blob right here. It must be coupled to that right there. And that's actually, let's see, this is green ortho set here, these two hydrogens here on this molecule, is coupled to the green meta ones right there, which are a little bit upfield from it. Yep, right there to there. And you can see here the black ortho ones is right here, and the blue lines show that correlation right here to the black meta peaks over here. Yeah. And this lets you see instantly what's correlated or what's coupled with what. And oftentimes that can be hard to determine, but COSY lets you do that. And it's not just limited to proton-proton correlation, but here's proton to C13, or heteronuclear correlation spectroscopy. This lets you see which hydrogens are on which carbons, which can be very useful for doing the full peak assignment of all the signals within a structure to make sure you've got the right thing. So here's the C13 data. Can't really tell which is which until you do the head core experiment, then you can see which ones correlate to which positions in the proton NMR. So here's the proton NMR with its peaks correlating these lines here in the field to the carbons that it's attached to. So it's a very powerful technique that lets you see what's coupled with what. All right, let's do some more experiments here, or problems rather. Well, let's experiment with the problems, of course. Some of these numbers don't correspond. I may have numbers from an older version of the book, but here's one here, there's problem 54, and it's actually, 5 problems, A through F there. And, look through those, and let's do a couple of these. If you want to pause now and give them a shot, if you haven't already, we can do a couple of these. It'll also review for test 4. We'll do more NMR, of course, and problems that way. But let's see this first one here. What do we have? Yeah, come back down to the board there. So or part A, there we had singlet, 6 H's, and it has singlet for 2H, and the shifts were 1.87 and 3.86. So what can we have here? We've got singlets, right? And we've got methyl CH3, we've got 2 of them. And then we've got a CH2, also singlet. And that's a little tricky to figure out there. We've got 2 bromides, C4H, what do we have? 8 Br2. First thing you can look at is units of unsaturation here. We've got, how many units of unsaturation? We've got none, right? Well, wait a minute. 6O2. Oh, well, we add the 2 halogens as if they were hydrogens, right? So this would be 10 for the purposes of doing the degrees of unsaturation. So 4 to 10, yeah, you can see that would be 4 times 2 plus 2, yeah, 10. So no double bonds or rings. So how do we figure this out? And this makes sense here. 2 methyls, there's the 6 hydrogens, and 2 up to the 8. But how do we assemble this structure to have this type of thing? And maybe the key here is the CH2 here has a shift of what? 3.86 delta. And that's pretty far downfield, you could say. Well, that might be, well, there must be a bromide on that position right there. But look, there's no neighbors here, okay? So what do we have? We've got a carbon here, 2 carbons there. So that's 3. So where's this 4th carbon coming in? Well, maybe it's a quaternary carbon. Maybe it's a carbon with no hydrogens on it. We might have the 2 methyls, and then what else do we need here? Bromide. So I kind of stepped through it there to arrive at this structure, but this is a 1, 2, 3, 4 carbon, a butyl group, right? And we have it branched here. We have the 2 methyls on the same carbon. So there's symmetry in this molecule. And notice they have no neighbors, so singlet, and then singlet here. That's really the only way to be consistent with this data. Okay, so that's A. Let's do a couple more here. B is an interesting one also, I think. B has C3, H, what, 6? Yep. And Br2. And the data is a triplet and a quartet. Okay. 2.4 for the quintet, sorry. Quintet, so it's a 5-line pattern, sorry. And 3.5 for a triplet. And wait a minute, there you're already looking at something, okay, C3. Okay, so maybe there's another quaternary carbon that doesn't have any hydrogens on it. And what are you told here about what these are? Well, you're not even told the integration of those, which makes this a little bit harder. Except you can see here a 5-line pattern. So how many neighbors does this have? You go backwards, right? N-1. So the number of neighbors here must have what? 4 neighbors. Okay. So where are the 4 neighbors? Well, maybe in this triplet, right? So let's see. How about if we have this type of structure? And again, we've got some symmetry involved here, right? So this is really integrating for 4H. It's not shown on the problem. But 3.5, these are both the same here, and they have 2 neighbors. So yeah, that'll be a triplet due to the 2 neighbors right there. And what about this? So here at 2.4, which is further upfield, right? 2 neighbors? No, 1, 2, 3, 4. So that turns out it's a quintet, a 5-line pattern. And yeah, it's consistent with that. There's really no other way to arrange these 2 bromides on a propyl unit to come up with anything that's not consistent with that. But this is a little bit tricky, I think, due to the symmetry here. This is the same as that, okay? So when you got that symmetry, that can be a little tricky. And this one is too. This one we just did, A here. we've got the symmetry there. So even though these are simple little fragments here, if you draw out what the fragments could be and begin to connect them up, you'll begin to see some. Let me skip over C. That's similar to the one we've done already. Let's go to D. And then we'll show you the structures here and look a couple more, and then that should be it for today. Let's see, D. What's the rest of the data there? We've got a triplet at 0.8, 6H. Yeah, 6H. Triplet. Okay. Yeah. And what do we have at 1.0? We have, sorry, I'm looking back and forth here. 3H singlet. Yeah, there's four here. This one's a little bit harder, I think. 1.5. And we've got a 4H quartet and 1.6. We've got, sorry, 1H singlet. Okay, now this one starts out with a couple things I think you can hang your hat on right away. 3H singlet at 1. Is that one we've been talking about? Yeah, so that's probably just a CH3, right? Okay, and this one, 1.6, 1H singlet. Now that, might be an alcohol. Oh, and yeah, we are told in the IR, we're given an IR here, yeah. This is 3300. Okay, so which one makes sense for this to be the alcohol? Well, the one that's 1H. Okay, so there it is, alcohol. Okay. And what else are we told here? But let's get all the data on here. I think that's it. Oh no, you're given the formula. Oh, they made it easier on you. Okay. C6H what? Let's see here. 14? Oh, okay. Yeah, that simplifies things. Actually, it makes it look even more confusing because look, we've really only got 1, 2, 3, 4 signals, but we're told we've got 6 hydrogens. So all of a sudden, these two here are a little bit trickier. But if you think about this, what?
All right, let's continue on.
Okay, give it a shot. All right. So yeah, we left off finishing up this part of the problem. Triple quartet says what? It might be an ethyl group, but it's not 2 to 3, it's 4 to 6. And plus we need more carbons, so maybe we have 2 ethyl groups, right? Now let's add it up here. We've got alcohol, and we have to put a carbon on that somewhere. We can't put the alcohol in any of these fragments. And so we have 1, 2, 3, 4, 5, and we need a 6th carbon here. So maybe it is a quat carbon, okay, with some other groups on it. So let's just put them on there. Let's see. Put on that carbon the 2 ethyls, and put the methyl and the OH. And yeah, this molecule will have symmetry to it. Right in the middle here, these 2 ethyls will be the same, and that should be the molecule there. If we go back up here, real quick, Isaac, we can see the problems, the solutions to this problem. There was A on the upper left, and I think B is the next one down. And then over there is D, the top one on the right is the one we just did. The other 2 there, the ester one we did similarly. The aldehyde sticks out. The diisopropyl ether is kind of a tricky one because of the symmetry there. You just see the 2 propyl groups. So again, symmetry plays a role there. Let's just do one more, and this is a homework problem, I think, and we'll do it at the board, and then I'll show you the spectrum for it. It's this problem right here, where you're asked about this ketone. And this ketone has a double bond right here, and you're asked about this hydrogen here and this hydrogen here. And they label them A, B, and they label these 2 as hydrogen C. And you're told that this one has a shift 7.0 and this one is 6.0 delta. And so why is this one so much further downfield, more de-shielded than this one here? Well, again, it's a resonance effect. Let's draw a resonance structure here and see. So it doesn't turn out to be too bad. Once you do that, you get like this. Okay? And so this hydrogen here, B, is on a partially positive carbon. So that will be shifted what? Downfield. This one's always on an alkene carbon, and that's in the alkene region, it's 6. The other thing to notice here is the IR of this molecule. It's 1690 inverse centimeters, which is low compared to a normal ketone. If this was just a regular ketone, it would be what? Up around 17, 1720, 30, whatever. Why is it 1690? Why is it a lower frequency in the IR? Well, it's because the bond order is reduced here. If we invoke this resonance structure, that is now appearing as a single bond. Now, it's not a true single bond. That would resonate carbon oxygen single bond at 1200. But the character of this true molecule has this bond order reduced from a pure double bond with bond order of 2 to being somewhat less than that, and it resonates at a lower frequency. So that part I think you can do. And part of the problem too is to come up with these J values here. This would be a triplet right there for that J3 relationship. And right here, you got the cis relationship here between J, A, and B. And you can figure out, I think, the rest of the problem there. And I think we'll leave it right there. You should have enough to solve the rest of those problems and work on quiz 9, which is again due not today, but the next class period. So check that and make sure you got that done. And zoom in to office hours or recitation, and we can help you out there. So very good. Hang in there, and we'll see you next time. Thank you.